Hello everyone. So this is all about the first order differential equations of the FP2 module, and even though some of this does contain some of the C4 material, what you'll see is that we're going to start incorporating extra things as well. So in class we'll talk about classifying differential equations in terms of whether they're homogeneous or non-homogeneous, what order they are, whether they're linear or non-linear, etc. But for now, let's just focus on this idea of a first order differential equation. Can we solve it by the means we have in C4 already? And let's have a look. So if we had something like solve dy by dx, y times dy by dx equals x, 1 minus x. Well, is this solvable at the moment? Yes, it is, because we can use, as you should have predicted, we can use this idea of separation of variables, i.e. we can split this thing, and this is what we should be thinking of this as in the general form. When we can use separation of variables, our general form has to be when dy by dx equals a function of x times by a function of y. This equation is in that form if I move my y over. So I'll have 1 over y, there's my function of y, and my x, 1 minus x, this will be my function of x. So it is in the form of separation of variables. And of course, if we were to carry on with this, we get 1 over q of y dy integrated with respect to y, and then our p of x differentiated with respect to x. So this is normal. I recommend that you always try and get your differential equations in this form first, and that way, well, dy by dx equals first, and then you can assess, is this a separation of variables problem, or is this something else, which is what we're going to go on to now. So let's look at this first order differential equation we've got here. Now, if we try our methods, and remember what I just said, let's try our method of seeing whether this is separable or not. And what I said was we would move everything over to the right hand side and get dy by dx by itself, which is what we have here. Can this be split into our q of y, p of x format? No. The answer is no. I cannot. There's no way I can separate the variables here. I can't individualize my two functions. So therefore, our separation of variables method is redundant here. We can't use it. We need something else. And this will lead on to the integrating factor, but let's look at this left-hand side here first. Let's see if we can do this intuitively. My idea, remember, is to remove the dy by dx. We need to find our general solution. That is going to involve an integration somewhere. But first off, we need to recognize something about this thing here. Do you notice that if we differentiated xy, if I do this implicitly, I'm going to get, by the product rule, x stays the same, y would differentiate to dy by dx, and then the next one, y would stay the same, and x would differentiate to 1. Yes, this thing is exactly the same as this thing, i.e., I'm saying that d over dx xy, which is our left-hand side now, is equal to cos x. So if I integrate both sides, xy, integrate both sides with respect to x, what you end up with is an easily solvable problem, because if you are differentiating xy with respect to x and then integrating it again, in a sense they're inverses of each other, aren't they? If you do something to something and then go back again, you're going to get what you started with. So you end up with just xy equals, and now it's just a simple integral of cos, which as we know is sine x plus c. And our general solution now becomes 1 over x sine x plus plus c over x. Easy. Now, this type of function that I've just dealt with here, this is called an exactly differential equation. So if you can spot that your left-hand side is in the form of a product rule, so an implicit product rule, then you can use this trick. But the majority of problems, of course, are not in this form. And this is why we need the integrating factor proof in order to show that if it's not in the exactly differentiable form, we will make it in the exactly differentiable form. Let me show you by another example here. Okay, so this example, we've got, again, our first order differential equation. You could try and move everything over to the right, like I said, to put this in the form p of x, q of y. And what you'll find is you can't. So this is not a separable problem. Again, try it yourself just to make sure that you believe me. Also, let's see if this thing looks exactly differentiable. Well, remember what I did before? I've got d over dx. Let's test it. So I know that this thing on the right needs to be y, because y will always differentiate to dy by dx, which is this thing here, right? Which means something needs to be here. Remember when we used the product rule, the something here stays the same, doesn't it? And then it times by the differential of y plus y stays the same differential of this thing here. Let's call that question mark. I don't know what that is. And it's not obvious to me what it is. It can't be 1, because 1 would differentiate to 0, and that means that term would go. This is quite difficult. Maybe this thing needs to change form in order for me to do this. Maybe I need to times it by something in order for this to work. Well, let's think about it. Let's think about perhaps timesing everything by, I don't know. Let's times everything by cos, let's say. So cos x dy by dx plus y, and now tan x would become sin x equals x cos squared x. Let's try this now. So d over dx, let's get my y, that has to be there, doesn't it? Cos x here. If I differentiate cos x, that's going to go, well, differentiate this thing first. Let's do it in order. This y differentiates to dy by dx. That's cool. That cos x, that's going to stay, so everything is happy so far. And then we've got our y is going to stay, and cos differentiates, though, to minus sin x. Right, so we're not quite there, are we? We're not quite there. What happens if I changed this thing to a minus, though? So minus cos x times y. Let's test that. Well, if the minus cos x is there, maybe I need to times everything by minus instead. Let's try this one. Minus cos x dy by dx minus y sin x. And then I'm going to make this thing minus cos x here. So let's try this again. Okay. So minus cos x is going to differentiate to sin x y, because minus cos x goes to, so cos x goes to minus sin x, so minus cos x goes to minus sin x, which will make sin x, and our minus cos x would stay the same, and dy by dx would differentiate. So we're still not there. No, it's not obvious for me to guess what I need to times everything by to make this exactly differentiable, and this is why we need this idea of the integrating factor, because the integrating factor is going to help me find the thing that I need to multiply everything by to put this in a form that I can make it exactly differentiable. So let's prove that. Right, so what we're saying is that we're going to say let there exist a function I of x, so a function of x called I of x, such that if I have a differential equation in the form dy by dx plus a function of x times y equals q of x, then if we multiply by I of x, we create an exactly differentiable differential equation, such that, so what I'm saying is that I would have, if I multiply everything by this function, I get I of x dy by dx plus f of x I of x y equals I of x q of x. And if this is exactly differentiable, then we'll see what happens. Okay? So let's have a go. I'm saying that if this is exactly differentiable now, if this function exists, then what should happen is that d over dx I of x times by y should differentiate to what's on the left-hand side here, if this is the case. So this should give us I of x dy by dx plus f of x I of xy. Let's change this left-hand side then and actually differentiate this. So if I differentiate my y first, so I get I of x dy by dx, plus, and this time my y stays, and then I'm going to get I prime of I of x. And remember, this is equal to our right-hand side, if this is the case. So let's look. If this is this, we've got I of x dy by dx both sides, that's fine. We've got y both sides, that's fine. But for this to be true, I prime of x must be the same as f of x I of x. This is looking promising. Let's carry on. So, if that is the case, then what I can do is I can start manipulating this and writing this as I prime of x over I of x equals f of x. If I integrate both sides with respect to x, can you see the connection I'm going to have here? I prime over I must be ln of ix equals the integral f of x dx. Remember, ln integrates if it's in the form of f dash of x over f of x because of its differential reverse chain rule there. So what we're going to have is, we're just going to move that over there, move that over there. To finish this off then, what we're saying that I of x must be the same as e to the f of x dx. Notice why it's called integrating factor, IF, integrating factor. So, we've done it. We've said that if there is a function I of x which exists, it is in the form of e to the integral of f of x, i.e. what I'm saying is that d over dx of I of x y, remember from our starting point over here, is our left-hand side, which must be the same as I of x q of x. And therefore, how do we finish this thing off? What we're saying is that we have, if we integrate both sides with respect to x, remember if we differentiate both sides and integrate it, we get what we started with, and we're going to be left with the integral of I of x q of x, where I of x is the same as e to the f of x dx. So the integral of e to the integral f of x dx, q of x dx. And it's proven. We'll just quickly see how to use this, okay? Okay, so how to use this. Is this in the form of dy over dx plus f of x y equals q of x? Yes, it is. It is in that form. So therefore, we can use our integrating factor method. First off, we need to know what is our integrating factor. We know that I of x from our proof is the same as e to the integral of our f of x, which here is tan x dx. Remember, this is the same problem we started with earlier and just could not find out how to make it exactly differentiable because it wasn't obvious, and that's what we're going to do now. So the integral of tan x is the same as ln cos x with our minus 1 on the outside. Remember, differentiate cos x, that goes to minus sine x, so we need a minus, and if you differentiate ln cos of x, you would get minus sine of x over cos x, so we need that minus on the outside, and this therefore would be the same as e to the ln sec x, and therefore we have sec x here as our integrating factor. From our proof, we're going to go straight from I of xy then is the same as the integral of our integrating factor times by q of x dx. So what I'm saying is we had to times everything by sec x in order to make this thing work, rather than what I was trying to do before, which was times everything by cos x. We actually needed sec x, which makes more sense. So now we've got the integral here of our I of x, so this is sec x times by our q of x, which is x cos of x. So in the end we're just integrating x, which gives us a half x squared plus c. And remember, on our left hand side then we've got our sec x, which is I of x, y. And therefore our final solution, our final general solution, is going to be y equals a half x squared cos x, remember this is our general solution, yg, plus c cos of x. And